is we directly use these theorems. Okay, so we calculate this posterior conditional probability based on our given informations, right? So, and then when we make a decision, right, from this probability, in natural speaking, like we can think about it, we can choose the most probable, right? Most probable outcomes we are going to choose, and this one is going to be happens. So that means MAP, maximum of posteriori estimation, is that, okay, now you have future probability, event probability A is 60% and B is 40%. Then A is a little bit higher in terms of the probability, a little bit higher than B. So then we can guess or we can predict, or in the futures, A is going to be happen. So that is map like the estimations, right? And how can we calculate the map? Then we can just use this like the Bayes theorem equations, and we can guess like the in the futures event. Okay, this one is what we discussed last time, right? So and we had some like the calculation task. Then and after that, so using some Bayes classifier and applying some calculation task, then we use very strong assumptions, right? Some assumption such that attribute like the input features are independent here. Okay, so input features are independent. So that is this like attribute independent here. This one is like the basic assumption in naive Bayes classifier, and that's why we put here naive on this like the classifier. So we need a very strong assumption. Other than that, we cannot apply this equation to make the classification. Okay, so this is the why we are talking about the naive Bayes classifiers. Sorry about that. So let's move on to some so sorry. Wait a second. Annotation. Okay. Yeah. So let's talk about something. Some example. Okay. So this one is also we discussed about that. Okay. We have some weather information: sunny, cool, humidity is high, wind is strong. These are we call the attributes, and these each kind of things are is a kind of samples. Okay, sample 1, day 1, sample 2, day 2, and so on. Okay, right. Sample 2, sample 3, and so on. And each sample have a 1, 2, 3, 4 feature. Feature 1 is outlook. Feature 2 is a temperature. Feature 3 is humidity, and feature 4 is like the wind. Sorry about that. Wind. Then display tennis is our goal to predict. All these 14 days is kind of given data set of D, given data set D. Then based on this given data set, we want to predict the future event when we have a new features, when we have a new day. For example, how about day 15? Day 15 might be a little bit different from the day 14 and day 13. Then I'm wondering whether I can go play tennis outside or not. This is all I need. Okay. So, how can I go up? Let's move on to the next question. So let's just think about it from the previous example. What we need to calculate to apply naive Bayes classifier examples, we need to understand, or we need to extract a kind of patterns based on some situation. So first thing, okay, when we are going outside, then what was the probability of the sunny? okay? And when we are going to outside, and what was the probability of, like for example, cool, high. So for example, humidity is high, or for example, wind strength is kind of strong. What was the probability? And also, what is the entire probability when we go outside? This one is what we need to calculate, right? And all this information is kind of extracting of patterns based on my historical information. And same thing when we are not going to play outside, then what was the probability of for each attribute? Okay, all this information is kind of some patterns, right? Let's just think of very simply. Think about it. How can we calculate all this probability from this data set? For example, what is the probability? Yes, and we can very simply calculate it, right? Because we have 14, then we just count how many times you go outside. For example, 1, 2, 3, 4, 5, 6, 7, 8, 9. So out of 14, we are playing outside 9 times. Then this one is going to be, right, 9 divided by 14, right? Then this one is also 5 divided by 14. And how about each kind of things? For example, if the yes, what was the probability? Think about it. Total is 9, yes. And how was the sunny? Right? How was the sunny? Then if you go see, out of says yes, how many times we have a sunny? 1, 2, okay? 2 times we are sunny. Then this one is going to be 2 times, okay? Then also we can think about it 9, 9, 9 something, something, or something. Same thing. In the no, 5 times, okay? And how many times were sunny? Okay, we can very easily count from the tables, and all this information give a kind of some patterns about my, like for example, users, or if for example, if that data set is for my data set, then my like the playing patterns. Okay, so this is all. Let's move to the, then we just fill up all the informations, right? PS is 9, for example, 14, 9 divided by 14, and the wind is strong when I go outside, and then 3 divided by 9, and so on. So now I made like all kinds of patterns. But what I'm interested in is, okay, now I have a day 15th, okay, day 15th, like the weather. For example, outlook is sunny, temperature is cool, humidity is high, wind is strong. Then considering my previous pattern, if I have a new this weather data, then will I go outside or not? So which means now your X, this information, X is given, that what is the probability you are going outside? Or what is the probability you are going or staying inside, right? We can predict. And then next question is how we can predict. How we can predict these two probability. And based on this probability, we are going to choose most probable event outcome. In this case, yes or no. Got it? So let's say P yes is P sunny yes multiply P cool yes multiply P high yes multiply P strong yes and multiply what is the probability P yes. This is very exactly coming from Bayes theorem, right? Then our probability 0.0053. Similarly, P no X, then we also calculate probability in 0.02. Then the next step is we can compare those two things Okay, those two things like this one and this one, right? And the 0.005 is definitely smaller than 0.02. Then applying MAP, okay, applying MAP, you can think about it. The second one, so probably no is higher than probably yes. Then my labels, future labels, is going to be no. Okay, this is naive-Bayes classifying. But when we calculate this using this information, using these equations, can be done if and only if we have strong assumption about our all these four features are independent, and that's the naive-Bayes classifier. Okay, so this is the some naive-Bayes of classifier. Then, obviously we might have some questions. Is that what if we do not have some kind of independence across or among all the future, right? That is a very common problem and very very critical, like the some kind of drawback of these algorithms. Okay, so right in the many real world tasks, obviously some features x1, x2, and xn are not fully independent, which means there is no for example, the left term is not going to equal to the right term, right? This one is definition of the independency, right? So it does not establish the left one is the right one. So which means that there is some kind of limitations to apply the naive-Bayes classifiers in this day problem. But some kind of problem, especially some natural language processing, then the features is more frequently more highly be independent rather than the others. The case, then so still like the naive-Bayes based classifier is very widely or popularly used in the language processing. Okay. So, and another one is how about some like the conditionals probability problem. For example, navigation predictions, right? Conditional probability should be non-zero, right? Because we multiply multiple conditional probability. For example, like this, we multiply multiple different kind of conditional probability. But what if one of the like the features, one of the conditional probability is a zero? Then all the features are very significant. The probability is going to be zero, right? For example, we have very high value in the first term and high value in the second terms. For example, okay, high value is the first terms and very high value is the second term. For example, almost close to one, almost close to one, almost close to one, but zero. Then this one is always zero. Then even if this value is very low, like very low, for example, 0.01, something like that, but we can say always our prediction is going outside. No, why? Because this one is always end up with zero. There is some problems. Okay, there is some problems. Then how can we handle this kind of situation? Then we can, as a kind of remedy, we can also think about it. Conditional probability R, estimate these kind of things. For example, like here, let's say, let's define NC is a number of training examples, number of training example matched case. Okay, and N is also number of training example for all the cases. For example, like yes, okay, yes, and then so on. Then the prior prior estimate P actually we just like estimate like is it 1 divided by T. So this means the possible value, this T is a possible value of the xj. In this case, for example, like sunny outlook, what is the probability of the possible cases, and then we just put some weight of the prior, right? This one is a little bit different. Now we have a new term of the NP. So M is the weight vector, right? We put some weight vector, then in order to prevent have some zero probability, then in the worst case, even if we do not, we have a like zero value in here, for example, in database, there is no sunny, but considering like the some kind of, we just put some weight to the prior on the prior estimate. For example, in these cases, like think about it, we have like three different kind of things. Then each one is 1 divided by 3. So make some artificial value about that and make some small value in the like the denominator. So it then, we might have some non-zero conditional probability on certain kind of situation, for example, in AKJ. Okay, so it's a kind of some trick to have a non-zero values when we have a zero probability value. Okay, so let's just think about a summary, some comments about that. One of the main advantage of Bayes-based classifier, as you can see, is the equation is very simple. So which means very easy to implement. Okay, so that is the one kind of things. And also second thing is, although it is very simple, but in the practical way, it has been works very well in the many cases. So there is some kind of advantage, but we have a very, very serious disadvantage again, is that independent, right? Attribute should be independent, right? But other than that, we cannot actually apply this Bayes theorem to calculate the post probability, right? So there is we have a very strong assumptions. And second thing is like in the practical, like there exists some kind of dependency. For example, like in the symptoms, okay, symptoms. Then if the symptoms have some correlation with like the fevers and having a cold and so on, that kind of things. For example, if person have a fever, then also he is likely to have some cuts, then those two features, those two attributes might be correlate with each other. In the kind of disease cases also, if the person have some cancers, then other feature value also very highly correlate with some the other features in the disease, right? Then think about it, this dependency, right? This kind of dependency, cannot be like considered in the Bayes classifier. So the best practical tip when we are thinking of considering this Bayes classifier, then always check when you have a data set, you need to check dependency or independence across all the features. Then if you have some strong like the observations about the independence, then it's easy, and then you can very simply apply this Bayes classifier as one of your major classifier. Okay, so that is about some Bayes classifier. Is there any kind of questions or something confused about Bayes classifier? Right, so you can use a chat box, or also you can use some annotations as well. There's no questions?
Yes, any student have any query, you can simply unmute yourself and then ask, or you can write on chat box also. If you have any query in between, you can write on chat box and Dr. Bhuvan will respond after a time interval.
Yes. So I'm now open the chat box. So if you have any kind of questions, then don't please do not hesitate. Write down your questions. Okay. If we do not have any kind of question, then now I'm going to move on to our next topic.
Yes, sir. Yes, sir.
Okay, so next question is, let's just think about it. a neural network, right? This is one of the very popular neural network, and I also assume that all of your guys, or most of your guys, already got some background and knowledge about neural network through or from the other the coursework. But let's just have some very brief recap about the neural network. Okay, this one is some neurons, right? This one is some neurons. These are generally like the biological neurons in the human brain. Then this from this synapse, and this synapse from this synapse, right? The electrical, like biochemical electrical information is going through this kind of through this synapse, and then gives some activations in the neurons. Then this neural activation, we already know that this neural activation is directly related to the human cognition or human learning or human thinking. And in the big pictures, under the big picture about the machine learning area, so the engineers, we want to kind of mimic of this kind of some real brain model. Then one idea was, okay, how about make some mathematical or computer the algorithms behaving like the human neuron. That is the neural network, and we try to like kind of the model it about the human neurons, and that is some motivation about the neural network. So in here, so some electrical information, bioelectrical is coming to the axons and then delivered to the cell body, and then these many like complicated connected ones, the neurons active and do some like the logical things, then make some outputs. For example, like some making decision, kind of feeling, right? Like accumulating some kind of knowledge or some make some justification and so on. All these kind of things is done in the human brain. Then we have a same models, okay, like here. So many kind of the input is coming in, and there is some kind of one, like the entire processing. Then using some like for example, some like the complicated processing done, and based on some processed value, we make some output. So multi-input, one processing unit and output. That is a very simple, like the model of the neurons. Then, okay, let's just think about how can we apply this kind of structure in the machine learning area. Okay, let's just think about it. So the first thing we are talking about is artificial neural network. Artificial neural network, right? Then there are two kind of things. So one is neurons, and the other one is synapse. But in terms of the architecture, as you can see, these circles, colored circles, we can say a node in the neural network. So node in the network. And this line, right, this solid line represent some kind of connectivity between the node, between the neurons, right? So it's kind of some synapse in the actual biological neurons. So, but in this case, we call the edges or weights about this connectivity. So in other means, just defining this number of the nodes and the value of the weight that is making artificial neural network. Okay, so all the artificial neural network is making these kind of network structures based on the data set we have. Okay, so artificial neural network has some, in terms of the calculation of determining the weight of this connectivity between the nodes. So this weight and this connectivity is like same as some logical or thinking or decision making process in the neurons, right? Then again, the kind of the determine the weight. Actually, there are two different way. One is feed forward, and the other one is feed backward method. Then the feed forward, like the one of the oldest one is single layer perceptron and the multi-layer perceptrons. And the feed backward method is Cohen's like SOM, but here like the Bayesian regularized neural network, this one is quite brand new. compared to the other one. But this feedbackward network is in this day, many people are considering as like the major some kind of the methodologies to make the artificial neural network relatively easy to calculate or easy to like computations in the network structures. Okay, but just try to remember there are two kind of things. One is feed forward, and the other one is feedback neural network. And let's just think about some multi-layer neural network. So we have actually three different kind of layer we can define in the neural network. We can say some layer. So one is input layer, and in the middles we are hidden layers, and the other one is output layer. Then you can also think about it. Why this one is a hidden layer? Because the input layers and output layer is obvious. It's totally depending on our data set. Okay? For example, input layer is depending on data samples and the data dimensions, right? For example, how many features we have. Okay? Then the Y1 and Y2 is usually our like the target label to be predicted, such as in the neighbor's example, okay, playing outside or not, that kind of output layer. So very obvious, and we know that. But hidden layer is actually like concatenating all these kind of the multiple connectivity. So it is not easy to see what inside. There is some calculation. There is some. It is more like processing unit. Okay, processing unit. So some very complicated calculation is done, but it's not easy to see directly. And that's why we can say hidden layer. So very important, major like the calculations, but it is like the hidden between our input and output. Okay. For example, xi in here, x1 to xm in this case input layer, then there is like input, right, from the unit, right? For example, unit 1 to unit m. And this wxij, this one is connectivity weight to hidden layer. So if we have many nodes in the hidden layer, then think about it, there also exists more kind of connectivity, right? Or more like the weight vectors, like the weight vector is going to be very large, right? And our entire calculation process is much more complicated. But this node is also related to kind of degree of freedom. So we might have a more higher chance to get a correct prediction. So there is a kind of some pros and cons. So if our model is very, very complicated, think about in our neuron is very dense, then the people's the brain is more smart, very complicated. And if we keep only a few nodes in here, 2 or 3 nodes in the hidden layer, then we also have some less chance to get correct predictions. But the model, in terms of model and computations, is relatively easier than the many node cases. So there is some pros and cons. Okay. And also think about F is we call the activation function, because our final outcome is, either, for example, going outside or playing or staying inside, right? And from this like the hidden layer to this like the output layers, so we need to determine, instead of the sending the value directly, we like kind of filtering out about some activations. Okay, and the Z is activation value of the unit I, so which means after the activations, okay, we have some filtered value, and this YI is kind of final outcomes, right? For example, this one is going to be like it or like number 1 or 0, some kind of binary things. So from the continuous kind of values, after activate functions and all our calculation or summation of the calculation transform into some discrete or binary outcome, such as playing outside or not. Okay, so this one is some basic structures about the neural network. So let's just see some kind of a little bit detail. Okay, how many neurons? Right? What is it? What was the neurons? And in here, what we discussed, neuron is kind of node. So in here, how many nodes in the hidden layer, right? So the precise optimal number of the neurons, number of the nodes, right, in the neural network, still open question. So in the many cases, actually, we have relied on some kind of tuning. We change the number of the neurons, number of the nodes in the network, change it, and see what we still like the best number of neurons still, and then we just there is that one is most popular way. And depend on the degree of the non-linearity and the dimensionality original problems, right? Definitely because there are some kind of in the hidden layers, right? In the hidden layers, if again, as I mentioned before, if we have more and more neurons, more and more nodes in the hidden layer, then the calculation process is much more complicated. Think about it, why there are so many connectivity. Then the dimensionality and the non-linearity of the problem is going to be increased. And our problem, original problem, is how much is very complicated, right? For example, our like the problem is very easy problem, very like trivial, and we don't need to keep many neurons in the hidden layers. But our problem, our decision making should be done in the neural network is very complicated. For example, we need to consider many different kinds of information. Then we need to keep very higher level of non-linearity and dimensionality. Then we would like to keep like more neurons in the hidden layer. So problem is very simple and trivial. We keep small number of neurons. But problem is very complicated, then we keep the large number of the neurons, right? And also same things, highly nonlinear problem need more neurons and smoother problem need more fewer neurons, right? And the second thing is too many neurons, right? Considering our original problem difficulty, too many neurons is lead to overlearning, or sometimes we can say overfitting. It means, for example, in the learning perspective, in this day, too much information is not good for generalization. Okay, our final goal is that okay, now we have a data set, we extract a pattern. So in this case, okay, we are going to use this multi-layer neural network to extract the patterns, and these patterns must describe our data set as much as possible. For example, in our previous example, like here, in this case, neural network try to explain all these relationships corresponding to this plane outside as much as possible, right? This is some like the good, like the goal of the making a good neural network. But sometimes in real world situation, right, some of the data set might be wrong, might be noise, or might be mistakenly written down. Then, like the ultimate good model should ignore some kind of some noise. Like the model don't need to describe or extract the pattern from noisy or mistakenly like input data set. But if the model is very complicated, then the model also think about it, right? Oh, because there is no way the model automatically identify, okay, this one is noisy or not. Model also consider this noisy information as a true information. That is kind of the overlearning or overfitting problem. Then in the future, if you have a new data set, because our model contains some noise information, it might give some less accurate predictions, right? even if model is too complicated, let's occur predictions, right? Then it is actually, it's a little bit violate our entire goal. Our entire goal is not making the model as much possible, but we are like the correctly predict the future event as much as possible. That is our final goal, right? And to predict the future event, we are relying on this historical data set. But if we run the too much things, then that one is not good for our future cases. Think about it. Okay, this is some example. When you are preparing some kind of exam, and your ultimate goal to the exam is actually getting a good score, then the best strategy for you to get a good score, for example, this data mining course, your goal is getting an A. And the best or efficient or optimized way is just study related to your exam problem. For example, this one is actually encompass all these kind of things, but okay, you study, for example, statistics, you study the computer engineering, even if you study the biology for the neural network, etc. So you studied every kind of knowledge, then yeah, in like finally, that's such kind of study might be good for your entire like the careers, but getting an exam, getting a very good score in the exam, too much study sometimes make you confusing, right? Too much information make you confusing. So instead of the study as much as possible, do a study preparing the exam comprehensively, right? Based on the summary or based on the key point of the lecture slide, that might be more helpful to get a good grade. So which means choose like the very essence of the study materials or lecture material is much more helpful to get a good grade. Same thing in the machine learning, containing all minor information is not good for our future prediction. Why? Because if we have too much information, then there is also some probability is including noise it can be included. Think about it. If you have like the full chunk of the data set, full chunk of the information, then definitely the portion of the noise is very large. Then your model also studies some noise information. It's quite random, but your model don't know, oh, this is a kind of some pattern. Then that one is typically we call it overlearning or overfitting. So if our model is too complicated, in here there are many neurons in the hidden layer, then the model is very complicated and it leads overlearning, and it is not good for you in the future reproducibility or generalization. Okay, and conversely, right, too fewer number of neurons, the model is going to be too simple, then it also fails to capture all the informative or important patterns in the data set, right? So this is still open question. So we always should be very careful about what is the kind of some good number of neurons, or what is the size of the hidden layer, right? It could be, okay? Okay, then one list actually, and like for example, we need at least one hidden layer, but sometimes we can add multiple hidden layers like this, and also connect like this, like that, like this, like that, like that. So if we have like one or two more layers, then the weight is going to be up. Then from the input to output, we have more steps to be calculated. The model is very complicated, but practically, right, one layer are necessary, but insufficient in the most of cases, right? But in this day, some very complicated process, something like image processing, right? Image actually contain a lot of information, right? That the input dimension is very large. So making some decision on the images, then we need more complicated structures. Then we some come up with like 3 layers or 4 layers in the neural network, right? And the 4 layers are actually the favored in the pattern classification test in these days. And if we have many layers, then think about a network structure. Okay.
Hello. Yes, Dr. Won. I think there is some issue regarding audio. Yes,
Hello?
Smita madam. Hi, now you're audible.
Oh, okay. So how's the problem in the previous pages or this page? Okay, let's just go back to previous one. So let's just see. So now we are talking about how many neurons. Is it okay to start from these pages? Hello?
Yes, sir.
Page 21, this page, should I start from these pages?
I think whatever you are writing, that time their voice was lost. Otherwise, it's okay.
Okay, so I'm going to start from this page again, okay? In the neural network, one major big issue is to determine the number of the hidden lane. This one is directly related to some kind of model complexity. So we are going to handle with some kind of the actual example later, but think about this complexity of model layers. So complex means it requires more like the computation from the input to output. So in terms of the equations, think about it. So let's say some kind of inputs, then we have some functions, then this one is outputs. And the complexity means in the inside of the things, and also I would like to allow all of you guys also annotate in my screen. And complexity means there is a equation level of this f is much more like the many kind of the some computation. For example, very simple one, x1 plus x2 plus x3, also can be some functions, calculations, complex, and x1, x2 plus x1, x2, x3 plus x2, x3 plus enter some value to like 4 and 5, etc. So then the complexity is much more, like the equation is much more complex. It means, think about it, model is much more complex, mean have a more degree of freedom, more freedom to represent or to fit the value of the y. For example, the equation is only should be end up with a summation, some possible value to have a y is very limited compared with this complicated equation. then the degree of the complications is actually directly related to the number of these neurons. If we have more neurons in here like that, then we have more weight connected to these neurons, then we have more kind of the variables in the equation. More variable means, right? More variable means more degree of freedom, kind of. Okay. Then our key question is how many neurons, how the complexity level of our model should be. Okay. And what I want to say is still open question. There is no explicit rule to all this number of neurons is the best. There is no. Okay? So only we can do is just some kind of scaling by ourselves. Okay? So there is some one thing we can think about it. So like
sorry, Dr. Vaughan, I would like to interrupt here. I think there is no slide is not changing. The multi-layer neural network size, that is one slide is showing that not changing the last 10 to 15 last few minutes.
Yeah. So I'm now continuing because my voice was disconnected. So I'm now continuing this slide again. Okay.
Okay. Fine. Thank you.
Okay. So depending on the kind of the degree of the again. So depending on the problems, if your problem is complicated, then we're gonna keep very many neurons, or then you keep the very more complicated structures of the neural network. If your problem is very simple, very easy to see the answer, then you only can see the very small number of the neurons. Okay? Then why we are concerned about this kind of things? Because too many neurons lead to overlearning. Overlearning means model is too much complicated rather than the optimal. So it means the model, if the model is too much complicated, then it's likely to consider some unimportant information, or we call noise information. So model also think about it, that noise is a kind of patterns, or kind of things we need to study. Think about it, right? When again, the major example is when you are preparing the exam, okay? The best way to get a good grade of the exam is just study comprehensively. Memorize or try to understand key essence for the exam. But if you read all kind of textbook from A to Z, then your brain is, your head is too much complicated, so sometimes you might miss to study for the exam. Not your entire kind of the knowledge accumulation, but for the exam. Right? Same thing. In the machine learning, the best way is when we are making the model, the best way is to our goal. If our goal is accurate prediction, then all the model should be built for that kind of purpose. But if the model is too good, too much complicated, it may works in your given data set, but may not be good for your future data set, right? But in the machine learning application, final goal is showing a good performance, not showing a good performance on the data set in my hand, showing a good performance in the future. So when you are doing some experiment in the lab, no, the final goal is when you apply this machine learning algorithm for another data set, new data set, it should be work. So that is a key concern. Same thing. Too much complicated, maybe work well on your data set, but not good for your future data set, right? Because it might contain some unnecessary kind of stuff. So that is overlearning. And in the neural network, if we keep many neurons, many number of the neurons, then definitely our neural network is going to be overlearning. Conversely, if you have fewer number of neurons, then our model is too simple to get answer. For example, when you are preparing the study, you prepare for example, when you are preparing your exam, you just studied very too much comprehensive level, very abstract level, then you might not solve the problems correctly. Okay, so that is some very key issue about that. So in the one hidden layer, most of case is okay, right? But in sometimes we can keep 3 or 4 layers, right? Then in this day, because the task to apply neural network is much more complicated. Think about it in autopilot systems or drone controlling. So it requires more complicated logical structures. Then, think about it. So we need more relatively more complicated structures of the neural network. Got it? Then complicated in the more layer means okay, this is a single layer problems, but more layer means if you have same inputs, but layer 1, hidden layer 1, and another hidden layer, and another hidden layer, and output layer. Then think about it, number of connections, number of synapses. This multi-layer, right, 3-layer has involved more larger number of synapse connectivity. Then our equation, in terms of our equation, think about some logical thinking. Second neural network, there are more number of the variable is more than for example 10 times higher compared to the first one. Then we have more higher chance to get a correct answer, much more complicated. Then we can say this one from the input to output, we can say a depth of the neural network. And second, many layers neural network, then we can say the depth is much more deep, so much more deeper neural network. Then that is in this that we call deep learning, right? Okay, neural network, we have many layers, so much more deep, right? Then may not be good or efficient for simple tasks, but work very well on the very more complicated tasks, such as image recognitions, right? But the drawback of this deeper neural network is you can think about many weights, many synapses to be calculated. So calculation is difficult. But in these days, we have developed the computation or calculation algorithm developed so much things from in last couple of decades. So now we can use a deep learning for more complicated tasks. Okay, so this is some neural network. Okay, then let's just think about it in the major functions, activated functions or activation functions. So here, now once from the inputs and then going through the hidden layers, then everything is going to be represented as some kind of summations of our input and the weight. But our final goal is just making a decision, something like going outside or not. But how can I link the weighted sum of the input neurons to the outcome? In the naive-Bayes classifier, we just calculate the post probability, and such post probability, we just define that, if to probability we calculate 2 outcome and the probability that, this one is, if then our decision is A, right? So then this is we call MAP. Right? But this is a kind of activation. from the probability to some kind of discrete decision. Same thing. Now our weighted sum is, for example, 0.98 for example, 5, something like that. Then how can you say, for example, in the link to playing outside of this number? That is activation. Then some activation function, say, if we input these activation functions, right, the value to some function, this function say, oh, now your value is 0.985, then it is linked to playing outside. That is a very simple activation function. So there is very different kind of activation function depending on the structures, but the most like the simple one is linear activation function. Just summations, just sum everything's kind of linearly with all these kind of the different weight summation. We just calculate linearly. So in here, for example, let's say, for example, like here, we can say, very simple one, x1 multiply w1 plus some value and some value in, for example, let's say this one is going to be input some summation of this one, right? And in this case, also x2 multiply w1, 2, and here xm multiply wm1, then we sum them up, all this value, and based on this summation, we make some decision, activation function f. Oh, the summation value is, for example, bigger than 0.5, then your answer is something. How, or if you want to make some problem more complicated one, instead of linear sum, maybe we can think about a nonlinear sum. For example, x1 multiply w11 square plus something, right? Then there is some nonlinear activation functions. And also a squashing effect is that the more formally prevent accelerating growth of the activation level through the network, which means if our network is too many neurons, then all this summation value is going to be too large compared to the scale. Then we need some modification to scale down over the number. But you think about it, our final sum, we're starting from 1 or 2, like 10 decimal point, but after some calculations, the output is going to be 1 million, 2 millions, then there is a very big gap. Then we need to keep some like the similar scales of the numbers. And most of cases we call the sigmoid. Sigmoid function in these days very popularly used. Sigmoid function is like that. So which means if the value is bigger than like the positive, then we are saying that yes. And then also if the value is smaller than something, then we say no. It is a sigmoid functions, right? And this one is very popular. Why? Because the sigmoid function is very easy to take the derivative in terms of the calculation. So this is a little bit out of scope of my lectures, but if maybe in the future, if you think about why people are using the sigmoid function, it is easy to calculate. Got it? So let's move on to the next things. Okay, this is some sigmoid. As you can see, okay, if the value is based on the 0, if there is something up, then you can see some value. So think about this one is our outcome. Okay, this is some outcome is yes or no. Let's just think about it in the binary classification. For example, we are playing going outside or not. If the value is in here bigger than 0, then our answer is going to be played yes. But just bigger than 0 but very, very close to 0, then even if you can say, playing go outside, yes, but I'm not sure. But our value is very large, then very close to 1.0, 1.1, and then it kind of probability, yes, definitely playing go outside. Same thing, minus, okay, minus, but very close to 0, for example, minus 0.01, then yes, technically, yes, you are now staying in your home, but I'm not sure, right? Very less like kind of confidence. But our summation value is very large, for example, like -10 or something like that, then definitely yes, you are going to staying in the home. Okay, so that is some sigmoid functions, right? So majority of the artificial neural network actually use some sigmoid function. Why? Because smooth, continuous, monotonically increasing means, think about it. Smooth, continuous, we can apply derivative. Then that is, we can say differentiable. So, okay, we can apply differentiations. However, if our activation function, right, if our activation function is some kind of like that, right? Then think about this point, because of this point, this one is non-smooth, right? Non-smooth. Non-smooth, what is the problem? We cannot apply derivative. Then why we are thinking of derivative, we are talking about a little bit later, but this derivative is going to be used to estimate the best weight of the connectivity in terms of the optimization, right? We are going to minimize or we are going to maximize some kind of fitness of our data set. Then in order to figure out some maximized points, we actually happen to use, we used to apply derivative. But if the sigmoid function is like kind of this non-smooth, then we cannot consider derivative, then our optimization problem is much more complicated. But sigmoid functions, smooth, continuous, monotonic increasing, which means derivative always positive, and very easy to identify optimal point, right, in the calculation. So why we use a sigmoid function? Easy to get a solutions in the neural network. Okay, so that is the main reasons of the using the sigmoid function in real in this day. Got it? And the other function, okay, this one is a linear function. So just summation up and below than something, over than something, we can say yes or no. And the symmetric hard limit transfer function is just bigger than something, we can say yes. Other than that, just no, right? Very simple. There is no confidence. And this settling transfer function is that less than something, we can say no, less than zero, less than no, and bigger than zero, we have some kind of some negotiation range. Then after that, yes. And then tangent functions. Tangent function is also kind of like to think about sigmoid functions. And the log sigmoid function is look like that. What is those two difference? Because tangent-based sigmoid function is having some value in the negative -1, but log sigmoid function is cannot have the negative value. So in some problem situations, sometimes we prefer to use this tangent function. Why? Because the range of the y-axis is more large. Then we have a more like kind of the separable or distinguishable the value in terms of the y, our decisions. But sometimes we might have a negative, so calculation might be a little bit complicated. But in the log functions, relatively easy because always positive point. But think about it, the choice is always between 0 and 1, right? Then sometimes we might, our solution is might tight up, okay? And the other functions. Then let's just think about it, some practice. Okay, here, now our input feature, first one is, let's say, some persons, some test level. And second feature is another test level. So based on those two informations, right, I'm going to determine some final level of the student, for example. Think about it. Oh, you have in the midterm, for example, you have 100. But second midterm, you have 50. Based on that, what was my final like the grade, for example, pass or fail, something like that, right? And let's just think about it here. The weight is determined by 0.25, and second one is minus 1.5, something like that. Then how we can fill this value? What is this value? Is anyone write down something? Because all of you guys now annotate in my screen. So please write down some value. Yes, someone do something, right, in here. So I'm going to give 5 minutes. Right? So here, how the value is going to be? No one? No one here? Okay. Let's just see, maybe let's just think about it. First thing, 1 multiply 0.25 and 0.5 multiply minus 125. Okay, this is a connectivity. So 1 multiply 0.25 plus 0. Minus 1.5 is minus 0.5. Okay, then we apply this value as our activation function. What was our activation function? Sigmoid function. Then minus 0.5, I'm going to put minus 0.5 here. And after my activation function, then I'm going to have 0.3775. Okay, so that is our final outcome of this hidden layer, right? And if we know other weight on this kind of gray line, then we can fill up second and or third node in the layer, hidden layer, right? The first one is 0.3375, and second one is 0. Something, third one is also the another value. And our final conclusions, our final output is going to be consider all these value in together, and then based on this number, we are going to make one decision. Okay, now we are talking about that one, second thing, right? So input and output, right? For example, here, we have these are input and these are the output. For example, if the input is 0, 0, then output is 0. Input is 0, 1, then output is 1. 1, 0 is 1, and 1, 1 is 0, right? Right. So let's think about it. If the 1, 1, then some calculation final outcome is 0, right? Then we now assign the weight of all of the synapse. What was the synapse? Right? The connectivity, right? The edges. Okay? Then this weight, let's say this weight, I just think about it some random. For example, I put some numbers randomly, right? And the initial weight, right? Between the 0 and 1, but right, this one is just kind of random things, right? Maybe it is going to be bigger than 1, something like that, but let's just think about it here. Now we have a weight. Then, like these examples, we can fill up the number over here, right? How can we do that? For example, in here, 1 multiply 0.8, right? And then also 1 multiply 0.3, right? Sorry, 0.2, right? Because in this case, in here, first one, sorry, 0. 0.8 multiply 1 plus, for this case, this guy, 1 multiply 0.2, so this one is 1. Is there anyone to fill up the value over here using some annotations? Second and third one, right? Can you, for example, how about this? How about here? Right? You can now draw some things on the screen, and anyone's write down some value on here. Okay. Okay, great. Okay, so let's see. Actual one here, correct, right? 1, 1.3, 0.8. And next steps, using this 1, 1.3, 0.8, we're gonna move next layer, right? Right. So we put this sum smaller in the circles, right? We're going to use activation functions. Next step is we are going to use activation function, right? For example, like this. So which means I'm going to put this number into activation function. Then we are going to use sigmoid functions. Then one, for example, first case is 1 divided by 1 plus, that is, and the other one is this and that. Got it? Okay, this is what we got. Next step, obviously, multiply this one. 0.78 multiply 0.3 and 0.79 multiply 0.5 and 0.69 something. Okay. Then final one is, if we simply calculate that, that is 1.2. Then apply ours one is 0.77. But think about it, our intended output is 0. But through all this weight, we end up with 0.77. Okay. So why it happened? Because we just using this random number. However, if we choose all this weight, because this input is given because our feature, right? If we choose this number nicely, very nicely, then maybe our target outcomes and the calculation is going to be very close, very close. So here is the thing. We use a random set of initial weight. Then the output neuron is a little bit far from the actual output. So weight setting determine kind of quality of the neural network, how good it is. That is a quality of the neural network, right? Then next step is, okay, let's try to find a very good weight. Good weight, lightweight means those two values are very similar. Okay, how? Backpropagations. This is some mathematical algorithms about that. Then, what is a backpropagation? Is backpropagations learns by iteratively processing a data set of training tuples, comparing the network prediction which tuple with the actual known target. Similar weight is, simply speaking, we calculate the difference. For example, 0.77 and 0 minus, what is the gap? 0.77, but sometimes we might end up with some negative value. So in order to prevent this one, let's just define our weight. Our final outcome is going to be this value, right? Let's say this one is y we calculated and original y, for example, in this case 0. Okay, this is some quality. If this one is small, our neural network is very good. If its value is very large, then our neural network is not working well, which means these values should be corrected. So my goal is that I would like to find all these values which minimize this number, okay? And that is backpropagations, the goal of the backpropagations. Clear? So minimize mean square error between the network prediction and actual target value. And start with some small random weight. Why? Because this one is iterations. We tried one, is not good, then we move next steps, try to figure out the better one, right? That is we call iterative processing, right? So errors of the output layer first, find the margin of the error output result, then back out the necessary change in the input sum in the previous layers. So that simply speaking is that firstly, we calculate the output, right? And for example, actual value. So for example, 0.77 and 0, something like that. So that is the OJ is output, what we calculated, and TJ is actual value, right? Our final goal is to reduce the gap. The second thing is we want to figure it out, this OJ, right? Then second thing is we apply some derivative about this, like the changes, error term. Why? We are moving forward to, let's say, for example, TJ minus OJ square is our final goal. And so this is objective, let's say this one is error. Okay, and error. What is our control? Our weight. Our weight. Then we have a many weight. We have a many weight. Then think about it. The best one is making this one is 0. Then in terms of the weight, our error term is going to be 0. Okay. Then we would like to calculate this one and some mathematics. I'm not going to introduce very detailed. Let's think about it. Some error function can be defined like that for each neuron, right? For each neuron in the output layers. Got it? Then weighted sum of errors of the neurons connected to the neuron J in the next layer are calculate the error in the hidden layer. So from at the last, we calculate the errors. Then we change the weight vector slightly to see minimize this error term. For example, in here, now finally we calculate that. Then let's just try to adjust the value of 0.3, 0.5, 0.9. And we slightly change the value. Then how we can change the value? Whether our derivative is going to be decreased, right? Because we have this one is multivariate, so it is not simple to just finding out one single variable making derivative equal to 0. Why? Because there are many variables, right? So like maybe if you have some background about some Newton method, right? Then iteratively changing the value to follow the directions to finally arrive in the minimum goal like this. Okay, this is entire functions. Sorry. Like here, and we are moving to here. Then that is derivative or our error term and a certain value in here, this, like weight is negative. So here. Okay, so that is systems, right? Weight vector connected to the Wj to the neuron K in the previous layers, right? And this is the directions. So our weight Wij is changing. How far? This amount, delta. And how this delta is coming from? This error function. So what does it mean? Oh, if you change this amount of the like the kind of the delta amount in the Wij, then our objective value is going to be decreased. Alpha is some kind of some learning rate, so let's just do not think about it more details. Then every time we apply this one we consider this one is iteratively, then all the Wij is going to be changed. How far? What is the kind of direction? Change it, and this changing lead minimization of our error terms, right? So this all delta in the previous epoch, small, some threshold, right? Some threshold, right? Then percentage of the misclassified in the previous epoch was below some threshold, or the pre-spiced number epoch has expired. So all three things is that every time we change this weight to decrease our objective function, but some kind of thing. First of all, the changing the value, current Wij is 1.0, but next Wij is 0.9995. Very slight change. Then we can say there is no possible change. So you need to stop it. So if you repeat multiple times, there is no change of the Wij weight, then your final objective is also is not going to be changed. First thing. Second thing, although Wij having some changing, but final objective value does not change that much. Then, which means now you are in the kind of some like the very large optimal area. No matter how you change your weight vectors, weight value, in terms of a final quality, for example, the final gap in here with 0.77, next time is, for example, 0.7666999 something like that, no more changes. Then we also stop it. Third one is just run some number of iteration, right? I only run 100 time change. That's all, okay? Three kind of conditions, okay? Let's think about some backpropagations of these algorithms. So first, think about it. This is all we had before, and this is what we got here, right? The next steps, I want to change this value to reduce the gap, those 0 and 0.77. So error 7's first case is according to our case is, for example, like think about it, 1 minus 0.77 and 0 minus 77, and so final one is minus 0.136. And second thing, right? Second thing is, think about it, what we did, right? We also consider like these equations, think about it, this error, the other errors. Now, for example, error 6 to error 5, then we are going to end up with, right? Here, this value 0 point, right? 0 point, like, I'm sorry, minus 0.136 is going to be another one. Then second time, we have another error 5, right? You got it? How about error 4? How about error, for example, when we apply error 4, think about it, how about error 4? Then, same thing, 0 point, error 4 is here, right? The error caused by these neurons, 0.79, multiply 1 minus, how was it? 0.79 multiply minus 0.136 and 0.9 something. Same thing, error 3, only what we need to replace, 0.69 to 0.73. Okay, so we can just repeat all these calculations, and finally we have 0.6, 0. Error 6, error 5, error 4, and error 3. Okay, we just calculated all these kind of things. Got it? Okay. Then let's say our learning rate is 0.7. This is some given parameters. So you can keep any kind of the number what you want, but at this point, let's say we are just using alpha is 0.7. Then update the weight. This updated weight is that currently 0.3, right? For example, here 0.3. Now I want to change this value to decrease this number. And this number, right, actually coming from here, then considering, think about it, the weight is all this weight, for example, sorry about it, error, neuron 3, let's say error 3 is minus 0.008. Oh, this amount of the error is coming from node 3. So if we reduce this number, if we change this number, then we can reduce the contribution of the error coming from node 3. My idea is, okay, changing this value, weight 36, to minimize the error caused by node 3. Then changing the value is 0.27. If you keep this number from 0.3 to 0.23, then your final outcome error is going to be decreased some amount. Same things 46, and you can apply all these kind of things. Just change the value. Got it? For example, let's think about it. 46, right? For here. How we can do that? This one. Original one is 0.5. 0.5 multiply running rate and error term minus 0.136. This one is original error terms from node 6 and 0.79. What was the 0.79? This one, 0.79. Then W46 original value is 0.5, but reduced one 0.42. So if you keep this one, then definitely we can guarantee that our final error 0.77 is slightly decreased. So let's just apply all these kind of things together, right? And we just very simple math. We're gonna end up with this number. As you can see, most of case, our number weight is decreased. Then, if we apply this number, all this weight number in here, all this number, then calculate. And I'm pretty sure 0.77 is very, very close to 0. I will leave up to your guys for your self-practice, but see how the backpropagation updates the weight and how much our objective value target is improved. This is a very simple backpropagations and to make a very good neural network. And this backpropagation, as you can see, very simple, just iteratively automate very simple calculations. Then even if you have very large number of nodes and edges, all this calculation is literally very simple. And that's why in these days, many people can use deep learning. One thing is thanks to the kind of computations, CPU, memory, GPU, and so on. The other one, this backpropagation. Very simple calculation algorithm to update the parameters in the neural network. Right, and most of the deep neural network, deep learning, use this backpropagation technique to get optimal outcome. Think about it. For example, in this case, we just represent number. Very simple examples about the neural network is face recognitions. And this input is, think about it, the location of the eye, location of the nose. Then this outcome is, for example, male, female. Then good neural network is that, okay, depending on the location of the eye, location of the nose, in the male people, then this outcome also say, oh, based on this location of the eye, location of the nose locations, this image represents male. If you put the female, then neural network is female. Okay? This is some examples about the neural network. Got it? So some deep neural network model 2000, like the 12 AlexNet. Okay, so this is some very simple history about the neural network. AlexNet, actually deep neural network is developed before than 2012. But the Alex, actually the people, his name is Alexei something. Actually, he was a graduate student in the University of Toronto. Then also he was working on this kind of very large neural network. So deep neural networks, many number of layers, many number of the neurons. Okay. And he actually applied like some kind of the competitions hosted by Google about handwriting images. If you just have a time, just Google it, handwriting images. Then you're gonna see so many handwriting numbers. And every year, Google's, right, have some competitions in the world. Okay, think about it. Submit your algorithm to recognize this handwriting correctly. Handwriting written by 0, then algorithm say this is 0. 1, this is a 1. That is handwriting competitions. And before then, most of the image processing algorithms, right, just using some naive Bayes, or we are talking about in later support vector machine, some other image processing technique. But this Alexei, he actually working with some neural network, and he developed convolution layers of the neural network. We are not handling that one that much, but adding some layers, some kind of, we call it convolution layers, and put them into the original, like the large deep neural network. Then this neural network show like remarkably, right, great performance rather than the other one, other algorithm, more than like 10% higher, dominate all these previous competition winners. Actually, that changed the light. And this AlexNet showed the potential about that. Oh, in the image recognition, image processing, deep neural network with a additional layer developed by Alex show very high potential. And from 2012, and the deep neural network apply all different kind of things, image search, like think about drones, like airline, and in this the autopilot in the, for example, Tesla, all these kind of the image recognitions or AI based on this AlexNet. Of course, more advanced versions, adding more some the other like fine-tuned features, more advanced calculation technologies, more well-defined layers. But anyway, that is something like, think about it. For example, like the change the world. Okay, so that is the one thing. And after that, so many kind of the net, some XNet has been developed. It's all of things are based on the neural network with some convolution layers, right? And so many improvements, and so on. Right now, the error term is that, think about it, from like the 2010, the handwriting error, the best reported error was almost 70%, but see, AlexNet shown 16%. After a couple of years later, LessNet actually shown less than 5%. So, right? So the one big breakthrough over here. So before then, no one used neural network as image processing, but from the AlexNet, many people using some neural network for deep neural network, many layers neural network, reading some extra layers, and so on. In this day, even though like 7 years ago, right? Many layers with some this kind of neural network we call the less network. So less residual network is that keep many layers. Then model is much more complicated, right? So it has some high risk of the overlearning and also very difficulty in the computations. The residual network, this kind of things, you think about LessNet, involves some very advanced level of calculations, also very good data reduction techniques. Then also it keeps some very like the practical level of the computation time, as well as very good performance, like the classification performance. Okay, so there is some some revolutions in the network, and there is what we call the ImageNet classification. So if you are interested in, just Google it about the ImageNet, and you can see all kind of images. Okay, and I'm going to show some examples about deep neural network in my research. One of my research was that we have a new medical images, like regarding some kind of follicle, in the human thyroid, right? And this follicle and the non-follicle area is a boundary of the thyroid and the non-thyroid. So one of the surgery in the thyroid, right? The concerns about the physician is that how can we easily see the boundary of the thyroid and non-thyroid? Because they do not want to take some out on non-thyroid area. Doctors, think about it. Maybe you may know or not, there is many like the cases when we are taking the surgery cases is that doctors take some our like the body organs out. Actually, it is not supposed to be taken, right? Think about it. Okay, this is let's say, okay, this is a human body, some area, human body area, like a stomach, or the other one, or thyroid. And let's say this is some cancer area. So the best situation is when we are taking surgery, doctor exactly take this out. But think about it, very difficult to see, very difficult to see. So they using some imaging technique, they using some microscopy to identify some dangerous area. But most of the case, when we have a discussion with many physicians, doctors, because make some robust, make some safety way, what they did is sometimes they just take this out. If we have a large area to take them out through the surgery, yeah, definitely yes. The dangerous area, cancerous area is going to be out. So we take some cancer out from our human body or from my organs. Second issue is that how about this one? This area. This area is actually healthy area. But this colored area also took out. So that one makes some very difficulty for the surgery after surgery. So some very old people have very difficulties about recovery because so many things also took out. Then one of the doctor's concern is that how can we draw, how can identify a very good boundary of the cancer? It is difficult to see the human eyes. Is there any way or very fast way to identify this area? And our research was focusing on the human thyroid, and we found out that the follicle is one key factor as a boundary of the thyroid and non-thyroid. Then we developed some deep neural network image processing algorithms to classify. Once we have images, then the algorithm say this is a follicle, this is non-follicle, very in real time quickly. And we use like the BGG based models. And as you can see, we got almost like 97 or 99 accuracy to classify the follicle and the non-follicle area, right? This one is finally like the plugged into some image processing, the medical imaging machines, right? We call the OCT images, right, about this one. And then these images about this one is actually 3D images. Then how can we apply this kind of things into 3D images? Then segmenting out follicle and non-follicle in the 3D images, 3D sample. Then the problem is much more complicated one. And using some existing technology, the accuracy was 82. In the 2D cases, using some existing technology, we still get 98%. But in 3D images, existing image processing technology, the accuracy is only 78%. But deep neural network model with many layers, then we almost got 100% correctly to segment out thyroid and then non-thyroid or muscles or parathyroid area very clearly. Okay, that is some applications of the neural network. Is there any questions so far about the neural network? If you do not have any questions, then I'm going to move on to next topics. Otherwise, because this one is deep neural network, so you guys already familiar with or very high interest about some neural network. Any other questions? Nope. If you don't have any questions, then I'm going to move next session. Dr. Berra, so when is the session ending time? It is 9:30?
Now it's just a few minutes, 5 minutes. I think that's okay.
Yeah.
Because 10 o'clock is
okay.
as per our 10 a.m. in here in India.
Okay,
It's
okay, I
okay.
see. Yes. So now I only have 5 minutes. Okay.
Yeah.
Yep. So let's just think about it. Next time we are learning about support vector machine. This one is very, very, very popular support vector machines. And also I'm going to introduce some basic concept of the support vector machine and also some example about the research, recent research based on support vector machine done by my research group. So that is another one. And then in the next time we are finalizing some classifications. Again, the classification itself is very broad, more than 100 different kind of method in this day about the classification. But now we are more focusing on very fundamentals, logics of a support vector machine. So we learn about naive and we learn about the neural network and then the basic concept of the deep neural network. Then we are going to learn about some support vector machine. And after that, we also learn about some ensemble method, right? And that is a 4 very big branch of the classification. And a week after, now we are moving forward to some clustering method. And in the meantime, if you have any questions or when you are, I'm going to like also think about it. All this lecture is also recording. So in the future, if you are see some my recorded lecture, if you have any question, then just do not hesitate contact me. Any kind of normal student question is going to be welcome. So please answer any kind of question if you have. Okay. And so I'm going to finish up my today's lecture. And thank you for your time. And even if like this one is Saturday morning, so now you can enjoy your time with your family member, with your friend, and have a wonderful Saturday.
Yes, sir. I think
Yeah.
it's time for today's session is over. Thank you, sir, for sharing us valuable lecture where we discuss about support ANN, artificial neural network, navy bias classification problems. On behalf of Computer Science and Engineering Department, Nirma University, I would like to express my sincere thanks to Dr. Vaughan for delivering such a